Again, it's great to be here, and thanks for those of you who came through the torrential rain. So today I'm very excited to tell you about. Oh,
It's okay. For those who are on Zoom, we can't see your questions throughout, so we will answer the question at the end of the talk for everyone else. You can ask them throughout.
cool. All right, so today I'm excited to tell you about a curious phenomenon, something we found so surprising we had to check it over and over and over again just to make sure we were convinced it was correct. And before I start, I'd like to emphasize this is all joint work with my PhD student, Henry Shugart. He's only 2 years into his PhD, very impressive, definitely a name to keep your eye out for in the future. Okay, so to set the stage, today's talk will be about min-max optimization, which is different from standard optimization min-x of f of x. There you have one type of decision variable, x. Here we have two types, so x and y. X is trying to minimize, y is trying to maximize. They're in competition. When you first think about competition, maybe you start thinking about games. So that's, of course, what von Neumann did 100 years ago when he first formulated two-player zero-sum games as min-max problems. So imagine Guy and I are competing. So I'm going to choose some strategy X. Guy's going to choose some strategy Y. After we choose our strategies, there's some payoff. I'll pay Guy some amount. If it's negative, he pays me. So I want to minimize how much I'm paying him. He wants to maximize. We're in competition. Okay, so that's one classic application of min-max problems. Of course, min-max problems come up in many other applications. For example, generative machine learning. So in GANs, the idea is you want to train a neural network that can generate fake images which look plausible. How do you measure plausibilities? So the approach taken in GANs is you train a second neural network which can detect whether the image is fake or not. So all in all, you are training two neural networks, a generator, so model with parameters x, and a discriminator, so model with parameters y, and they're really trained in competition. And at least, I guess, 5 years ago or so, this was a very popular approach for generative machine learning. Min-max problems also come up in other machine learning applications. So perhaps all of us have seen examples where we have an image of, I don't know, say a panda, and then someone comes along, Linnea comes along and adds an imperceptibly small amount of noise, and all of a sudden the classifiers freak out. They say, not a panda, it's actually an airplane. So such classifiers are said to be not robust against adversarial perturbations. And a recent trend in machine learning has been, well, to train classifiers that are robust. And the basic idea or the basic approach is to solve a min-max problem rather than just minimize the classification loss. So here the max is modeling some adversarial perturbations. To an optimizer, you could say this is just a example of robust optimization, optimizing under uncertainty. In many other optimization domains, like if you have constraint optimization and dualized constraints, you have a min-max problem, et cetera, et cetera, et cetera. Full disclosure, I intend to say nothing more about applications in the rest of the talk. The rest of the talk will be about some more fundamental questions about solving min-max problems in the abstract, but I want to at least give a sense of where these types of problems arise, so you have a sense of why people care about these problems so much. Okay, so we'll talk about algorithms for solving min-max problems. So first we better clarify what it means to solve such a problem. There are different types of solution concepts. You could ask for a stationary point, which is a pair of x, y, so the gradient vanishes. You could also ask for a saddle point, so a pair x, y, such that neither person is incentivized to deviate, given that the other person doesn't. Today we'll focus on the fundamental setting of convex-concave functions, so the direct analog of convex optimization. In this setting, these two notions coincide. I'll use them interchangeably. And this should ring a bell to those who are familiar with convex optimization. You can either characterize a solution with locally as gradient equals 0, or globally, meaning you can't change your answer and get a better objective. Okay, so that's what it means to solve a min-max problem. We'll talk about today algorithms for computing such solutions. Okay, maybe I'll pause real quick, do a poll here. I guess most people are okay, well, Who here has worked with min-max problems in some capacity? Okay, about half of us, great. But hopefully everyone's played with gradient descent in some form or seen convex optimization, things. Okay, so let me start with just very briefly with one slide on a common background of convex optimization. Just to remind us what we should remember from algorithms for convex optimization, we'll move very quickly to min-max optimization. Okay, so imagine we have nice convex optimization problem. As simple as you like, unconstrained, convex, strongly convex, smooth, whatever. How would you solve this? Maybe one of the first algorithms you learn, or one of the first algorithms we teach is gradient descent. Let's see if we can zoom out. So simple iterative algorithm. Each iteration t, you have some guess the solution xt, and you try to improve it by moving in the negative gradient direction. So why that direction? It's the descent direction. Convex optimization 101 says if you move a little bit in this direction, you improve your objective. Okay. So that's gradient descent. Let me emphasize there is one and only one parameter here. So it's how far do you move, the step size. If you want to be fashionably, call it learning rate, same thing. There's lots of different ways to choose step sizes. Short steps, long steps, constant steps, silver steps, random steps, whatever. However you want to choose them, a key point is it's always got to be positive. Because if you have a negative step size, then you're going in the positive gradient direction, which will ascend, not descend. And even ChatGPT will tell you that's idiotic.
Oh, it does say idiotic, sorry.
No, but you prompted it. You said it would-
I could have just done this and yeah. Okay, so let's choose positive step sizes. And good news is that if we do choose positive step sizes, so basic fact, fundamental fact from convex optimization, if you choose positive step sizes the right way, gradient descent will converge. Okay? And that's all the background we'll actually need for the rest of the talk. But as a brief aside, let me mention that I stated this theorem for simplicity just about can you converge or not. Of course, you could ask more refined questions like how do you choose step sizes to converge as fast as possible? So as an aside, if you open any textbook in convex optimization, you'll see that they all prescribe the same thing, which is to use constant step size schedules, meaning in each iteration t, use the same step size alpha t. Not the focus of today's talk, but something just want to mention briefly, is something I've been very excited about the last, I guess, almost decade now, is there's an opportunity here actually if you use time varying step sizes, you can converge faster, provides an alternative mechanism to acceleration, doesn't require momentum or any other changes to the algorithm. You can do this either with deterministic step sizes, like these things called the silver step sizes, or with random step sizes, IED from a certain distribution. Again, not the focus of today's talk, but just want to advertise this briefly, something we're very excited about, happy to tell you more after. Okay, in any case, today we'll focus on min-max optimization. Okay, so X will always be the minimization variable, Y the maximization. We'll focus on the fundamental setting of F, which is convex and X, concave and Y, so convex-concave. This is the sort of direct analog of convex optimization. So how would you try to solve such a problem? Maybe one of the first things you would think about is, let's do the analog of gradient descent. Well, here X wants to go down, Y wants to go up, so you should do a descent step in X, or ascent step in Y, that would be the natural thing. So to avoid confusion, I've put signs here, the negative and the positive, so that throughout these step sizes, anything sensible would have these two being positive. That would be sort of the natural direction. X is actually descending, Y is actually ascending. Okay, so far, this is the problem, the direct analog of convex optimization. This is the, an algorithm, direct analog of gradient descent. What we just saw in the previous slide was that gradient descent converges. You just have to choose the positive step sizes appropriately. So should we expect the same thing to happen here? if I just choose these step sizes appropriately, will GDA converge? The answer is actually no, and maybe this is the first surprise when you start looking at min-max optimization. So turns out GDA does not converge, no matter how you choose your step sizes. Choose anything that's reasonable, non-negative. And this failure is actually, even on embarrassingly simple problems, even one-dimensional, so x and naught are one-dimensional, unconstrained, problems like x times y. So it's bilinear. It's not even like really using the full convex-concave sort of. Okay. You can see what happens. You can see this failure in pictures. Okay, so here I'm plotting horizontal axis is x, vertical axis is y. The unique solution is 0, 0. That's where you want to get. That's the only place where the gradient vanishes. I'm initializing here. It's the same picture if initialized differently, rotate, homogeneous, whatever. The GDA flow, so if I take step sizes to 0, it will just cycle exactly on these circles. Just follow these flow lines. With any positive discretization, it'll be even worse. It won't even cycle, actually diverge. So simultaneous GDA is the name I'll use for, I guess, updating simultaneously. So alpha t equals beta t is some whatever positive number. Be the analog of how you would typically discretize gradient flow to gradient descent. So this will actually not just cycle, it will diverge exponentially mad. You could try to be clever and do things about update one at a time, like first x and then y and then x and then y. So alternately alpha and beta are 0. That's called alternating GDA. That helps a little bit, doesn't diverge, but you're still cycling. The iterates are not getting to 0. Okay, so that's what happens in a picture. It's not hard, and it's insightful to think about, why this is happening mathematically. So the way we'll do this is let's just look at the GDA update, and we'll plug in f equals xy. Yeah, question first?
So is this impossibility for a constant step size, or is it any adaptive sequence of alpha?
Yeah, any. This is, I'll say something more formal later, but yeah, anything positive, no matter how you choose them.
Okay.
Yeah, for this problem. You could choose them time varying, asymmetrically, adapt. Yeah, so
Thank you.
it's a pretty universal failure. Yeah, great question. Okay, so we're going to try to now fit this picture to math, and we're just going to plug in f equals xy. So let's write down what the movement is. The x variable goes in the negative gradient direction. The y variable goes in the positive gradient direction. There's not many gradients I can compute in this world, but x times y I can. Okay, so gradient in x is going to be y. Gradient in y is going to be x. And so if we just plug this into the definition of GDA, which I have up top, then xt plus 1 is xt and moving alpha along this direction. Yt plus 1 is yt, moving beta t along this direction. I've concatenated these variables just because, well, now you can think about this as a linear dynamical system. So you can think about this as the next update, xt plus 1, yt plus 1, is an update matrix times the previous update, times the previous iterates, xt, yt. Right, so this 2 by 2 matrix we can fill in. It's very explicit. This thing here. And as we know, if you have a linear dynamical system, if you want to converge to 0, that's going to happen. Well, that requires the eigenvalues to be a norm less than 1, the spectral rates to be less than 1. So you can certainly compute these. They're nice and explicit, the eigenvalues. I'm going to be even lazier today because we don't even need to do that. We can just compute the determinant. Something we can just look at without doing any calculation. And the point is that if alpha t and beta t are non-negative, we have 1 plus positive. This is at least 1. So there's always some expansive direction. It's not going to converge to 0. Okay, so very short derivation of just why this is happening. If you think about this just a little bit more, you can convince yourself that actually this will apply not just to non-negative step sizes, but to your question, all sort of standard categories of step size schedules. So GDA fails to converge even on this like one-dimensional bilinear problem if you take a step size schedule that satisfies either 1 or 2 or 3, let alone any combination of them. So if you're always non-negative, you will not converge. If you update x and y symmetrically, you will not converge. If you use constant step sizes, you will not converge. And this convergence, or this does not converge, becomes diverge if the step size is non-zero, just because these are non-zero, you're actually adding a positive amount. This is strictly bigger than 1. And this failure is universal. You might think, okay, maybe x times y, like Jason shows, a really pathological problem. That's not at all the case. This happens for literally any bilinear problem, fit any coupling matrix B here, anything that's non-zero. This will happen on every eigenspace, this divergent behavior. Okay, so far the main point is just that we have the analog of convex optimization, we have the analog of gradient descent. It does not converge for min-max problems.
What if you regularize?
Okay, so hold that thought. So this is exactly what I was going to come to next. So it's important to, I don't want to confuse the story too much, but it's important to mention that there are some restricted settings where GDA does converge. So if you have strong additional assumptions like uniformly bounded gradients, or to your point about regularization, if you have strong growth conditions like strong convexity or strong concavity, then GDA does converge. But it's well documented in the literature, there are several sort of major issues with these types of results. So I guess first off, even if you do converge, it's provably at a slow rate. But let me not even focus on rates. There's sort of more important issues. First, these assumptions will preclude sort of simple settings like unconstrained bilinear or quadratic. It doesn't even capture x times y. And second, this result really requires averaging, taking the average iterate. And that's just a non-starter in applications like GANs or a machine learning where you have non-convex or non-concave objectives. They're the average iterate's just meaningless. And I'll emphasize this, these results really do require averaging. The raw iterates still diverge or cycle or cycle. Imagine the same problem we had before, x times y, but just constrained to a bounding box. Then you're in sort of these types of settings. You'll still get the same divergent behavior, only constrained by the bounding box. So the raw iterates are still not converging anyway. It really does require averaging to. Okay, so just to summarize, GDA does converge in some restricted settings, but even when it does, it'll converge at a slow rate, and it requires averaging, which is a major issue in many applications. In any settings beyond that, it does not converge, no matter how you choose positive step sizes, and even on simple problems. Okay, so this is sort of the lay of the land. Oh, question?
No, but slow rate is exponential, right? But with a flat constant, that's what you mean by slow rate?
So I guess it depends on the setting. You can play these different settings. So for example, for this one, for strongly convex, strongly concave, like it cannot accelerate, and there's some papers showing that, things like that. Yeah. Great. Okay. So because of these issues, the literature has really focused on changing the algorithm. So modifying GDA beyond just step sizes to make it converge. So there's been a very extensive literature, very fruitful literature about adding extra building blocks like extragradients, optimism, momentum. And there's been some very nice results. This can help GDA converge in theory, can get fast rates in many settings, can help in practice. And because of all this, the conventional wisdom, I guess for the last 50 years or so since Korpolovich, has been that GDA will not converge in its original form. You really have to add these extra building blocks. So our main result is that this folklore wisdom is wrong. What Henry and I show is that GDA actually can converge on all these classical counterexamples, unconstrained bilinear, quadratic, convex, concave, if you just use better step sizes. Okay, so the key innovation is what step sizes you use. So we propose some unconventional step size schedules, things we call these slingshot step sizes. I'll define what those are in a couple minutes, but for now, let me just emphasize there's sort of 3 key properties. And these are an exact parallel to the 3 things, the 3 standard categories you cannot have if you want convergence, right? So before I said if you're have constant step sizes, or update x and y symmetrically, or always positive. If you have any of those, let alone any combination, you will not converge even on x times y. So to even have a hope of converging, we have to break all of them. Okay, so maybe before defining these, let me just say in words what's the idea here. So imagine I'm competing again with Guy. So let's say Guy is the minimization variable x, I'm the maximization variable y. So normally he would just ascend, I would ascend, and we somehow cycle, we're not. Here's what we propose. So in the first iteration, Guy will descend like he's supposed to. So he does like a forwards, a natural step. I'm supposed to ascend, but I'm gonna be a nice guy. I'm gonna help Guy out. So I'm gonna actually descend. So I'm taking a backward step. It's meaningless for me, it's not helpful for me, but we are under the understanding that next iteration, he'll help me out. So next time I'll ascend like I'm supposed to, I'll do a forward step, and he'll do a backward step, he'll ascend. So first iteration, I do a backward step, next iteration, he does a backward step, and we'll just continue like this the whole time. So certainly it's time varying, asymmetric, sometimes negative. You can see it in a picture like this. This was my title slide. Let's see if I can move this around. Okay, so if you look on the right here, these are the Slingshot step size schedules we propose for bilinear problems. So here in black is the alpha t's, the step sizes for x. Here in gray is the beta t's, step sizes for y. Let me first just contrast this with a more standard step size schedule. It could just look like this. That would be the simultaneous GDA if I choose alpha t equals beta t as some positive constant. I don't even have two lines because this is both the black line and the gray line. And it's above 0. Okay, so here you see that the black and gray are, certainly they're not constant, so they're time varying, property 1. Property 2 is they're different. I have two lines, so they're asymmetric. And property 3, you see that's sometimes below 0. Okay. What does this do in practice? Okay, so here I've just plotted this for the very simple problem x times y we've had so far. What we see now is that in every other iteration, one of us could be doing sort of nonsense. But the key point is that after 2 iterations, we both make progress. So in one iteration, we might do something dumb, but after 2 iterations, we slingshot. The forwards progress outweighs the backwards progress. That's what we call the slingshot step sizes. Okay, so we prove it converges on bilinear, quadratic, convex-concave problems. Also can talk about rates. Turns out the rates are actually quite reasonable, even though that's not the focus. They're competitive, typically competitive, sometimes even exceed known rates for more sophisticated variants like optimistic, extragradient, momentum, etc. But today I'm not going to focus on the rates. You can read about them in the paper if you'd like. Today in this talk, I'd just like to focus on the conceptual things. Why is this happening? What's this phenomenon? Why is it not idiotic to use negative step sizes? Why is there any convergence at all? Okay, so the way I'd like to do this is I'm going to give 2 plausibility arguments for understanding how this happens, and not focus as much about the rates. Yeah. Okay, take questions with the meme on the slide.
So you have this graph of the choice of the step sizes. How do you choose the magnitudes of those things? They look very particular.
Perfect. We'll get there very soon. Yeah. So I'll mention just a little bit about optimal rates, and then I'll mention how. Yeah. Good. Okay. So plausibility argument 1. Let's return to bilinear problems, the sort of classic counterexample we've been talking about so far. Also because this is sort of the simplest possible setting where you can see really the benefit of negative step sizes. Okay, so this is the same problem we had before, x, y. I've just made it multidimensional. It's just, it's not any harder. I've translated the solution x star y star to be 0 like we had before, just without loss of generality. And just for simplicity, let's assume that the singular values are all positive. The general case is straightforward extension. Okay, so why are negative step sizes helpful for this? So let's start with the definition of GDA. Definition is always a good place to start. Let's plug in what it means to be a bilinear problem and try to see where the negative step sizes could arise. Okay, so this is my function, x transpose by. So the gradient in x is by. And plug this in. The gradient in y, b transpose x. So we have a linear dynamical system. We can write the next update as some update matrix times the previous update. And I'm really not doing anything so far. This is exactly the same as we saw before, just with, I guess, the number 1 replaced by a matrix B. Okay, so why is this helpful? So our first observation, sort of a starting point for us, is that every 2 iterations, something interesting will happen. So I'm just going to slap 2 update matrices together. This is the update from time t to t plus 2. I've just made it 0 to 2, so I have less t's floating around. So update matrix at times 0, update matrix at times 1. Okay, again, nothing sort of particularly interesting so far. This is more or less exactly what we had in the counterexample. So here's the magic, and I'll say it as magic first. Consider these step sizes, and later we'll see where these come from. So these are exactly the step sizes I was talking about before. I'm going to help Guy, then Guy's going to help me. So we pair every other one as positive or negative. So consider these for a second as magic, and let's just plug in. So alpha 0 is h, beta 0, negative h, alpha 1, so you have 2 negatives gets a positive, and so on. And the key point is that when you multiply these 2 matrices out, you get your update matrix for 2 steps, and this is a contractive matrix. This has norm less than 1, because BB transpose and B transpose B are both positive matrices, so imagine like a positive number like 5. And so if I do 1 minus some small step size times 5, you get like 1 minus epsilon. This is contractive. Okay, so this says that in every 2 iterations, we get some amount closer, some multiplicative amount closer to the solution 0, 0. And as a trivial corollary, I can just cycle this. We can repeat, I help Guy, Guy helps me, and so on. And we get exponential convergence. Well, let's just say convergence first of all, and then also exponential at the rate given by this contraction factor. Okay, so this is maybe our first proof today about negative step sizes can help you converge. Okay, to understand this result a bit deeper, I'd like to emphasize sort of the key phenomenon here, which is that in each iteration individually, the update matrix U1 or U0 can be expansive, well, actually will be expansive. You'll have norm bigger than 1. This is why we had the counterexamples before. But the key point is with the step sizes I told you about, the 2-step update matrix is actually contractive. Okay, so what's going on here? For intuition, I like this 2 by 2 matrix example. So imagine this is U0, this is U1. Both of these have norm bigger than 1. Their biggest eigenvalue is 1 plus epsilon for both of them. And yet when you multiply these matrices, you get a matrix which has norm less than 1. So why is that happening here? These 2 matrices, they both have 2 eigenvalues, 1 plus epsilon, an expansive one, and 1 minus epsilon, a contractive one. They both have the same eigenvectors, 1, 1, and 1, negative 1, but which direction is expansive or contractive will swap. So if you look at any iteration individually, there's some direction where you're expansive, but that direction will actually be contractive for the other matrix. So if you look at any particular direction, you could expand a 1 plus epsilon, but the other one will help you 1 minus epsilon. And together, they multiply, get a 1 minus epsilon squared, which is less than 1. Okay. I mentioned this as intuition. It's in fact not intuition. This is like literally what's going on above. If it's x and y are one-dimensional, these are literally what U0 and U1 look like. If you're in higher dimensions, you can diagonalize. This happens on every eigenspace. So this is the fundamental phenomenon. Just to summarize in words, in each single iteration, one of us is going backwards. So that gives some expansiveness to the update. But overall, in 2 steps, we both move towards convergence because our forwards is outweighed by our backwards. The 1 minus epsilon helps more than the 1 plus epsilon hurts. Okay. So
Can I ask a question? So when you look at the traditional fixes for this, the ones you're seeing people add momentum and things like that, and you look at the analysis, like are things like this popping up? Like is this kind of like implicitly what people are what's fixing things? Is this analysis what's relevant in that case? Or is it for a different reason those other methods are succeeding? You kind of see what I'm saying?
There is lots of different interpretations of many different methods. I think this is feels a little bit different than the things I've seen, but of course, when one starts talking about interpretations, many things can be argued to be similar, not similar.
Right, I guess what I mean is like
Think about this in a slightly different way for these other methods.
yeah, so I guess what I mean is like if you look at the traditional methods and you look at the way that they analyze things,
Mhm.
like is something like this kind of going on under the hood? Just maybe they're not like explicitly identifying what it is. Like is something kind of contractive going on in this sense in the traditional analysis? I'm just kind of curious.
I find it to be conceptually different,
It is.
but we can maybe talk more, especially when we talk about interpretations, that can have a long discussion. So yeah, there's maybe a lot more we could say, but the short answer is that I find this conceptually different. Yeah. Okay, good question. So to summarize, this is why GDA converges at least in bilinear problems. So later in the second plausibility argument, I'll tell you about why it could converge beyond bilinear. But before we do that, while we're at this stage, let me dive a little bit deeper into bilinear. I said we won't focus on rates, but let me just mention briefly, also to Ahmed's question. Now that we have convergence, you could ask how fast can you go, right? So we've said so far, if I choose these positive negative step sizes, this is the same thing we've had so far, just in a more concise version. If we choose this for small enough HT, then every 2 steps contracts. We get exponential convergence at some corresponding rate. You could ask, okay, well, can I take larger step sizes? Can I get away with that? Could I use time varying HT? What are the optimal step sizes? What are the optimal rates? So the reason I mention this as sort of more of a remark is that conveniently, all of these questions are answered just by reinterpreting the derivation we did above in the following way. So here's the key observation. This is just a reinterpretation of what we did before. It says that 2 things are equivalent, and I'll emphasize this is only possible with our step size schedules because you have to have negatives to have this cancellation. So this does not apply to other existing step size schedules. So first thing that's equivalent is 2 iterations of what we just saw, slingshot step sizes. The second thing is 1 iteration of an auxiliary algorithm, which you do not directly run. So it's gradient descent on the joint space where Guy and I stack together our strategies and actually collude. We can't really agree on who wants to minimize or who wants to maximize, but we can both agree that we want stationarity. So it's great, 1 step of an auxiliary algorithm on this auxiliary function. Okay, this is what's called the Hamiltonian. For bilinear problems, you can just compute the gradient like we did before and square, and it becomes a nice convex quadratic. And you can see why this is true. I didn't write the details here, but 1 step of gradient descent time quadratic, the update is identity minus step size times Hessian. So the X update would be identity minus step size times BB transpose, the top left block. The update for Y would be identity minus step size times B transpose B, the bottom right block. That's what we just saw before in the update matrix. That's why I said this is an equivalent reinterpretation. Okay, so why does this help with rates? Well, we've just reduced understanding the best step sizes for GDA to understanding step sizes on convex quadratics, sort of standard optimization. And so we can just look up, I think Young actually here at Harvard in his thesis in 50s proposed the optimal step sizes for gradient descent on convex quadratics related to inverse roots of Chebyshev polynomials. So if you just set h squared to be an inverse root, or rearrange this by the -1/2, those are exactly the slingshot step sizes that we propose. Okay, so I won't focus too much on rates, but I'll just mention, this gives you precise bounds. For those of you who like convex optimization, the square root usually refers to what's called acceleration, and these rates we get are exactly optimal, not just among all step size schedules, but in fact among arbitrary first order algorithms, no matter what extra things you use. So that's where the Chebyshev step sizes come up here. For x times y, For bilinear problems, you can see how this converges. Okay, so the diverging thing, as I said before, simultaneous GDA, this is going to never converge. If you do alternating GDA, it's going to cycle, so it never makes progress. Optimistic and extra gradient with standard parameters. So it's the green and purple, they're on top of each other. They are converging, they're just converging slowly because it's a poorly conditioned problem. With these slingshot step size schedules, you can get accelerated convergence. The only reason it doesn't exactly match the lower bound is because I'm doing it on a random function. You can choose a worst case function that'll exactly match. Okay, a couple of remarks. So first off, I just tried to explain this in its simplest form. This extends to different convergence criterion like stationarity or distance to an optimum. It also extends beyond bilinear. So if you think about what we used so far, where did we use f as bilinear? Well, we use the fact that if f is bilinear, then it has linear gradients. Because then you can write an update as a linear dynamical system, an update matrix times previous iterate. There are other functions in the world beyond bilinear who have linear gradients, like quadratics. So this will apply directly, basically no changes. You can also relax other things. This particular argument will not work directly for convex-concave. I'll tell you later how we do that, but I'll give intuition for it. Next remark. It was apparently an open question for these bilinear problems, how to get acceleration with more sophisticated variants of GDA. As a trivial corollary, since we get acceleration without momentum or extra gradients, maybe not the algorithm you actually want to run in practice, but at least from a theoretical perspective, this resolves this question. You can just use R step sizes and use zero momentum or zero optimism. Let me mention also there's a number of equivalent implementations of slingshot step sizes. There's a number of invariances where you'll get the same final iterate and therefore the same convergence rate, at least in exact arithmetic. So one thing is for bilinear problems, the update matrices are commutative, so I can permute the step sizes however I want. Let me focus on a different type of invariance because I think it's intriguing. So far I've just said use these 4 step sizes, positive h, negative h, Guy and my strategy will be equal and opposite, sort of as magic. But actually there's many more solutions, and it's really any solution of these 2 equations. So there's 4 step sizes, 2 iterations times 2 people. What are these equations coming from? So if you remember what we saw before, we want u0 times u1 to have this 2-step update matrix where the off diagonals is 0. That's the Brown constraint. We also want the diagonals to be contractive, so these to be signed a certain way. Okay, so any solution to this will lead to convergence for bilinear problems. Let me tell you maybe a different way of thinking of the second one that I find more insightful. In each iteration, the product of our step size will be will be negative. So one way of doing this is positive negative. That's what we've described so far. But I'll mention just as a remark, there's many ways in the world where we can have 2 numbers that multiply to a negative number. Another way is with complex step sizes. So it turns out for bilinear problems, you can equivalently implement everything I've told you about using complex step sizes. So perhaps surprising because the problem has purely real data. Okay, but I won't focus on this one as much today. Doesn't extend as gracefully beyond bilinear problems, but I just thought it was intriguing, so I wanted to mention it. Okay, so to summarize, we've now had our first plausibility argument, the thing I want to focus on most, seeing why this converges for bilinear problems. So in the second plausibility argument, I'll give you a complementary perspective, a different way to understand the 2-step progress. And an upshot is that this will extend beyond bilinear to convex-concave. Okay, a couple questions, yeah.
So I get the slingshot interpretation, but I'm just wondering, why does the magnitude actually increase in the middle of the schedule? I don't quite understand.
Yeah, good. So for bilinear problems, you can actually, the order doesn't matter. Everything's commutative. So the thing I showed was just a more stable ordering for numerical precision. So in exact arithmetic, it will not matter. again, for bilinear. For convex concave, the order does matter. But for the thing I showed you, we have an appendix where we show that if you do really dumb things like, don't think at all about the ordering, you can get numerical instability. This is a certain more stable ordering. Okay, I guess the very quick story is for convex quadratics, since the 70s, Lebedev and Feingold had talked about what's the best way of ordering Chebyshev step sizes for convex quadratic optimization. Since we've reduced that problem, you can just reuse that fractal ordering. Yeah, great. Jason?
Sorry, no, this is really interesting. I'm just kind of curious. So among all of the solution, or all your step sizes that satisfy those two equations, can you like kind of optimize among them, or like choose the good ones for a particular problem that will lead to, I don't know, better?
Oh, you mean adaptively? Okay, so in the worst case, for the worst case rates, the sort of magic thing that I mentioned, these Chebyshev things, that's actually optimal among, gives you exactly the optimal rate among all step size schedules, even among all first order algorithms. But maybe your question is about, can you adapt to particular problems and converge faster? That's a great question. And that's one of the open questions I'll mention. So maybe I'll
And those ones would satisfy these two. They would have to satisfy these two, right? Or are you saying that this is sort of for the worst case?
Those are what you would want to have the two steps make progress.
Mm-hmm.
There are other ways you can do this. We didn't try.
There are other ways.
Yeah, the full algebraic characterization of all sufficient necessary is more tricky, but since this already gets it, this is maybe simple. Yeah, you think? Thanks.
So if I remember correctly, I remember something like the extra gradient methods in some type of optimization problem is minimax optimal. Okay, but in your simulation, it seems that it's way off. So I'm wondering, like, is there anything I'm missing?
Yeah, great. So there's many different settings, and you can, for every setting, for every algorithm, you have a complexity. We tried to be not creative at all in choosing our settings. We just tried to take the most standard ones. So bilinear problems, quadratic problems, convex concave, Stirling convex, Stirling concave. For bilinear and quadratic, it was apparently an open question for extragradient to get accelerated rates. There are other ways to do this that change the algorithm even more. This gets acceleration, so it's actually faster than known rates for extragradient optimistic momentum. For Stirling convex, Stirling concave, extragradient does accelerate. We can also get exactly the same accelerated rate with just step sizes. For convex concave, I think we matched the rate as well. So again, the rate wasn't the main point, just converging, but actually we're getting pretty reasonable things without trying too hard. Yeah, good question. Okay, so thanks for all the questions. Let me move on to plausibility argument 2. Okay, so this will be a different way to understand the two-step progress. The overarching intuition is this in words. So we're doing positive and negative step sizes. The key idea is that these will cancel the first order, but you'll still move in some net direction, be a higher order net direction, second order. This net direction will move you towards convergence and is an otherwise impossible direction for you to move. Okay, it sounds very abstract, but I promise this is so intuitive you do it every day, or at least see it done every day. So every time you parallel park, okay, so if your car is here and you want to park, here, cars can't move sideways. It's not a direction you can move in. What you can do is you can move forwards, you can tilt your wheel, and you can move backwards, and you get closer to parking. So the forwards and backwards are the main movements, they cancel. You've moved somewhat, so you have a net direction that's sideways. It's a lower order direction, and it's towards convergence. Okay. So that's what's going on. That's the geometric intuition. Of course, you can quantify this. How do you quantify things canceling to first order? You do a Taylor expansion. That's what we'll do next quickly. But if you ever get lost, this is just the idea. Okay, so let's do a Taylor expansion. So let's consider two steps of the Slingshot step sizes just as before. Because of the signings, both of us are descending, and then both of us are ascending. So I can write this more compactly in terms of the concatenated variables z equals x comma y. In the two iterations, we're doing negative gradient, positive gradients. If these gradients were evaluated at the same points, they would exactly cancel, but they're not. The second one is evaluated at z1. So we can understand how different this gradient is. Well, z1 by definition is z0 with some perturbation. So the gradient is going to be the gradient at z0 along with some perturbation. by a chain rule. And so if I just plug this in, we can understand the two-step effective update. Okay, so you have part of Z1. This is that's the definition of Z1. And now we'll plug in the gradient we just computed. Okay, and you can see that the gradients cancel, positive and negative, just like we expected. So things cancel the first order. You're left with a second order net movement. Okay, so this is not a direction you could move originally and involve some Hessians. The appearance of the Hessians should, if you like finite differencing, this should ring a bell. Finite differencing, you typically cancel zeroth order queries to get a gradient. Here we're doing the same thing, sort of one level up. One way to think about it. Okay, so it's not a direction your car could move in, but why is it a helpful direction? So to understand that, we'll go back to so this is the generalization of the observation we saw before, and this will tell us why this movement is in a helpful direction. So before we saw that for bilinear problems, 2 iterations of GDA with our positive negative step sizes is exactly equivalent to 1 iteration of an auxiliary algorithm when we're colluding on this Hamiltonian. So before it was exact for bilinear functions, now it's approximate because we're doing tail expansion, but it holds more generally. So for example, convex-concave. Why is this helpful? Well, if this direction is just gradient descent on the Hamiltonian, then we're encouraging stationarity, right? We can't agree who wants to minimize or maximize, but we can both agree we want a stationary solution. Stationary solutions are solutions to our original min-max problem. Helpful direction. Okay, there's also many other nice geometric interpretations of this direction. For example, it quantifies the non-reversibility of gradient flow. If I do a positive gradient step, negative gradient step, I'm not in the same place. I've moved, I've drifted. You can also compute this as directional derivative of itself, et cetera, et cetera. But the main point so far is now we've seen a second reason beyond bilinear why this could be helpful. Okay, so let me finally define slingshot step sizes now that we've seen sort of these 2 plausibility arguments. And I'm going to, first thing is the optimal step size will depend based on the setting and parameters. So I'm going to define this in terms of a family of step sizes, satisfying 3 key properties. So property 1 is the negative step sizes. Oh, and as before, I'm thinking about paired iterations, right? So iteration 2t and 2t plus 1. Property 3 says you better go at least as much forwards as you go backwards. So far, we've had equal and opposite, exactly 0. We'll see in a second why it can be helpful to go a little bit more forwards. Property 2 just says that the net movement, so when things cancel, it's in a helpful direction. So we contract, not expand. So it's a bit abstract. Let me give you 2 concrete examples. So in the paper, we study 2 instantiations of this general family of step sizes based on whether the gradient is linear or nonlinear. For linear gradients, we do exactly what we talked about so far. Equal and opposite, I'll help guy, guy helps me. Maximally anti-correlated. For nonlinear functions, or sorry, nonlinear gradients, we do something very much the same spirit, but it turns out you want to go more forwards than backwards. I'll explain why in just a second. So we truncate the second negative step to 0. There's many ways to get convergence. This is just one particularly simple one for analysis. So there's only 1 negative step. We'll flip a coin just to break symmetry about who gets the negative. You can ask why have these 2 different things? It turns out for problems with linear gradients, this is exactly optimal rates, like we saw before, but actually fails to converge in general convex-concave due to some pathological examples. The idea is that if you have a function where the gradient is you have a function which is locally linear, then the gradient is constant. And so if I go negative, a negative step and a positive step of exactly the same size, I end up nowhere. I end up where I started. So the trick is just give yourself a little more oomph, go a little bit more forwards and backwards, which is why, this is one way of doing that. Okay, so I started much earlier about the sort of three key properties of these step sizes. I just want to go into a little bit more detail about them. Okay, this first one, I guess we've talked about a lot, the negative step sizes. Yeah, at first seems nonsensical, seems like it should only worsen the divergent behavior. But the key thing is that it's desynchronizing, so we can actually both agree to collude about some objective, the Hamiltonian. And this leads to maybe no progress in every single step, but progress every 2 steps. A second property, I haven't talked about this as much so far, but it's very important. It's essential that we're updating differently, x and y, so alpha t is not beta t. And conceptually, I want to emphasize this goes beyond classical reductions from min-max algorithms to monotone operator theory, where you traditionally concatenate your 2 variables, z equals xy, and treat them symmetrically. So it's this just highlights the importance of min-max problems are by definition, stated in an asymmetric way. It's helpful to actually use this, not just to always reduce to this more general class of problems. Okay, time varying. There's several ways to do time varying things, and this came up in one of the questions, I think Ahmed's. You can vary within pairs of iterations, so positive not equal to negative. That's what you need for convergence. If you want fast convergence, accelerated convergence, then you actually need to vary across the iterations, so these HT's magnitudes. Okay. So I think it's hopefully clear this is pretty different from previous work, but just to say a couple extra words. Some stepsize schedules have some of these properties, like asymmetry or time varying, but you need all 3 to converge even on x times y. So nothing before had all 3 properties in particular, nothing had negative. Perhaps the most syntactically similar previous thing is negative momentum, so proposed by this very nice paper of Goodell et al. So it's syntactically similar and that involves some type of negative movement, but it's actually fundamentally different. It changes GDA by adding internal dynamics, uses all positive step sizes, typically symmetric in time invariant parameters. Moreover, it was unknown if you could accelerate it for bilinear quadratic problems. It was not even known if it could converge at all for convex-concave. We get all of these for slingshot step size. So actually a different thing. And lastly, I'll mention negative step sizes seem like an essentially untapped opportunity. So I think they've never been used for min-max problems to our knowledge. We found 2 papers in the literature that have considered possibly using negative step sizes in a different setting for a different purpose. So they're thinking about standard optimization, min-x f of x, and they have in mind, they're using this for a different purpose, for non-convex problems. Their idea is that if you sometimes go backwards, you could escape your well. So they allow for, although do not necessarily use, they allow for negative step sizes in their line search. Okay, so again, different setting, different purpose, and I'll mention for convex problems, they would never use a negative step size. Okay, so we start a couple minutes late. Should I end fairly soon? Like in like 3 minutes, 5 minutes, 1 minute?
1 to 3 minutes is equivalent to me, so we finish nicely, but
Perfect.
we should finish in the next 5 minutes so we can ask questions and people can get coffee.
Perfect. Okay, so I wrote very briefly on purpose. I just want to mention just a little bit about what happens for convex-concave, and then I'll summarize. Okay, so as I mentioned before, plausibility argument 1 showed us why things work for bilinear problems. Doesn't exactly, can't directly translate to convex-concave, but much of the intuition, step sizes, and results will extend. As I mentioned before, we'll have to do some small change. So we'll have to do a little bit more forwards than backwards. That was the thing being sometimes, negative becoming 0. In plausibility argument 2, we saw that if it's equal and opposite, you get this new direction. Now that we have a little bit more oomph, now that we have a little bit more forwards than backwards, some of the forwards backwards cancels. That's the helpful direction sideways. But you also have some extra forwards movement. And that's your standard GDE update. Okay, so there's a convex combination of 2 different types of updates. It's essential that there's both types for convex-concave because both fail on different worst cases. Something we found very intriguing is that this combination of 2 things actually recovers consensus optimization, which is an algorithm proposed by this very nice paper of Mesheder et al. About a decade ago. It has been used in empirical machine learning to train GANs with great success. So There's some differences. They compute these Hessians with double backpropagation, so it applies for structured functions. Ours applies for general functions, but only gets approximate because we're doing a Taylor expansion here. Okay, I bring up this connection just briefly because it provides some maybe extra justification for why this is not such a crazy idea. We're recovering an algorithm up to high order, which apparently works very well even in challenging non-convex landscapes like GANs. But I want to emphasize this does not at all imply convergence of our step sizes. So there's been some very nice work about doing theoretical convergence of this algorithm, but it's fair to say it's still a nascent area. It's, for example, not even known if it converges for some simple types of problems like smooth convex concave. So we cannot directly use that. Instead, we directly analyze our algorithm, and we're actually hopeful that we can do the reverse, that our connection maybe actually can help explain why that algorithm works so well in practice. Okay, so the way we prove this is we have a different way of quantifying two-step progress, sort of along the lines of plausibility argument 1 and 2. Great, so let me finish with takeaways. So the way I started this talk is that we saw in convex optimization, gradient descent will converge. Just choose positive step sizes appropriately. And the folklore wisdom is that GDA does not converge if you use just step sizes. So the main result is that's false. You actually can converge on the key thing is to use better step sizes. They have to be time varying, asymmetric, periodically negative. You need all three properties. The key idea we saw several times in different forms is that in each iteration you might not make progress, but overall in 2 steps you make progress. So it's like a new direction you can't move directly. I think this new algorithmic phenomenon opens up a lot of interesting directions. I think it shows an untapped opportunity. My hope is that this can be added as another tool to the algorithmic toolkit, another building block to design algorithms. This talk focused on understanding it in its simplest possible form, just step sizes, what can we do? Of course, in practice, there's no reasons to tie your hand behind your back and say, I'm only allowed to use step sizes. So I think a very interesting question is, can this be seamlessly integrated or combined with more sophisticated things like optimism, momentum, extragradients? There's very rich and fruitful literature about why these things can be very good for different reasons. Can these be combined? Can we combine with silver step sizes? Can we combine with adaptive things like Jason mentioned? Many other questions. How general is this phenomenon? Can you get faster convergence in restricted settings? Et cetera, et cetera. Would be happy to tell you about more of this either now or offline. Thanks.